Okay, you're welcome to the second part of this class. So, where we'll be looking at other aspects of fluorescence spectroscopy. Now, we're going to start with absorption and emission processes. Absorption and emission processes. Remember, we said for fluorescence, the molecule must first of all absorb an electromagnetic radiation. And in the case of the examples we considered earlier, the materials or chemicals absorbed UV radiation and gave off fluorescence, either green fluorescence, yellow, red, or blue fluorescence, as in the case of diamond. Okay, so absorption first, and then fluorescence emission follows. So now the process for absorption, you can see S naught plus H nu giving S1. So S naught is telling us that's the ground level. So then plus the energy, that's the energy value. That's Planck's constant times frequency of absorption. So then it shows that the electron is excited to the S1 energy level. Next, we move down to fluorescence emission here. Now for fluorescence emission, remember we are already at S1 excited energy level. So X1, that's the excited state. So after vibrational relaxation, the molecule will give off the energy in the form of an emission. So that emission is what we call fluorescence. And then it will go back to the S naught. That's the ground state. So in case I ask you to give the equations that highlight or show the processes for absorption and fluorescence emission, you should be able to give me these two processes, these two equations. Now to Stokes shift. Remember we talked about energy for absorption and energy for emission. Of course, you can convert that into lambda, that's wavelength, right? So we know that from our basic physics. So now Stokes shift is simply the change in wavelength, okay, between the emission and the absorption. What are we saying? Remember, you will use a light or electromagnetic radiation to excite the electron. So that is where you have lambda absorption. So in the case of the diamond, for instance, okay, the UV light you are using is your lambda absorption. The lambda emission is the blue fluorescence emission you are getting from the diamond. So that's your lambda emission. So lambda emission minus lambda absorption is what your Stokes shift, which is your delta lambda here. So that is Stokes shift. So I can ask you to write on Stokes shift. Now this is very important, the quantum yield of a fluorescent material or a fluorescent chemical. So what is the quantum yield? So the quantum yield refers to is actually for quantum yield we are comparing the intensity of light, number of photons emitted and number of photons absorbed. Okay, so what we are looking at is the efficiency of the process. So if you are putting in so much of photons to get very little photon emitted, then your process is not efficient. So what we want is a fluorescent material that you just need to put in a little or sufficient amount of photons, and then you get a considerable amount of photons emitted. What can this mean? Okay, for instance, crime investigation. Okay, and what you are looking for has a very low quantum yield. That means even when you put on the UV light, you might not really see the fluorescence very well. That might be difficult to detect. So you might need a stronger UV light, okay, to and more intense UV light to get that fluorescent out. But if, for instance, the evidence you are seeking for has a very high quantum yield, that means with just the normal UV light, you will see the fluorescence even from afar. You say, ah, that is the evidence. So you need a high quantum yield. So what is the quantum yield here? So quantum yield, which you have there, is the number of photons emitted over number of photons absorbed. That is quantum yield. Okay. So this is the theoretical definition. But when it comes to practical definition, okay, so there you have it. So you have the Kf over Kf plus Knr and plus Kisc. So you have the equation here. Okay, you can see. So where Kf is the radiative decay rate, Knr is the non-radiative decay rate, and Kisc is the intersystem crossing rate. So this is your quantum yield. So in case I ask you to write on quantum yield, you give me both, okay? Now to fluorescence lifetime. Fluorescence lifetime. Actually, you will not be able to detect this with your eyes. It's just impossible for you to detect a fluorescence lifetime or the gap with your eyes. That is impossible. Why? Because the typical values are about in nanoseconds. Nanoseconds, like we are looking at um, billionth of a second. Okay, billionth of a second. That is like a second divided into billions. So you cannot see it with your eyes. So that is why when you put the UV light on the fluorescent material, you see the fluorescent emission nearly immediately. Okay, so it just comes to you immediately. But there's this tiny gap which you cannot see with your eye, and that is the fluorescence lifetime. Okay, so that is talking about, okay, the time between when you excite to the time when you uh, get your emission. So you have the uh, formula there. Next to we have the Beer-Lambert law in fluorescence context. When we talk about when I come around for that, okay, that's for molecular spectroscopy where we're talking about UV, you know. But I think other lecturers will talk about this. But Beer-Lambert's law, you're looking at the relationship between that's for absorbance, relationship between absorption and concentration. Okay, absorption and concentration. But also for fluorescence, there's a relationship between fluorescence and concentration, fluorescence intensity and concentration. Okay, so where F is your fluorescence intensity, this symbol that looks like E is this epsilon, and it's your molar absorptivity. C is the concentration. L is the path length. This small l here is the path length. I naught is the incident light intensity. So this k, small k here, is the instrumental adjustment to ensure that your work is accurate. So take note of that for the Lambert's law in fluorescence context. Now, the equipment, how does it operate? Okay, so there we talk about the fluorescence spectrophotometer. That is the name of the equipment. In case I ask you to give me a block diagram and a schematic diagram of the fluorescence spectrophotometer, this is what you are going to give to me. So there you have the block diagram, right? So light source, excitation monochromator, sample cell, emission monochromator, detector, and readout. Okay, now just below you have the schematic diagram, right? So you have the schematic diagram there. So schematic diagram, here you have the light source. Usually the light source is a xenon lamp or a laser, okay, as the light source. They have an excitation where excitation happens. Okay, so this actually excites your sample. So there you have your sample. So it excites the sample, and then after you have fluorescence emission, the fluorescence emission is captured. So you have the emission monochromator, and then whatever data it gets is passed to the photo multiplier and then the readout. So that's what you have there. But take note, for a fluorescence spectrophotometer, okay, it can work at different wavelengths. That is the strength. And that is why it is superior to a fluorimeter, for instance. So you can work at different wavelengths. I will talk about that when we get to interpretation and the likes. So now, so this is the schematic diagram. So take note of the schematic diagram. Now we come to the components. So the light source. So what are the light sources that can be used for a fluorescence spectrophotometer? Okay. So the common one is xenon arc lamp, right? For very common. Then another source that can be used is the laser. So laser is, so those are two common sources. Now to the monochromators. So the monochromators, what's the function? They select excitation and emission wavelengths. As I said, with the fluorescence spectrophotometer, you can work at different wavelengths. So the monochromator selects excitation and emission wavelengths. So they contain so you have the diffraction gratings. So next is sample holder. Okay, so the sample holder is usually quartz cuvette. So cuvette is the holder where you have the fluorescence. So and then uh, you have right angle geometry. So it's so that it minimizes transmitted light interference. So that's how it works. But take note of this, the type of cuvette used. So it should be a quartz cuvette, not glass. You have glass, you have polymer. No, so it should be a quartz cuvette. Why? Because the quartz cuvette is transparent to UV. So that's why you see UV transparency. Next, we look at the detector. Okay, so detector, you have the multiplier, photo multiplier tube, and the charge couple device, PMT and CCD. So those are the. So I can actually ask you a question to give me or draw the block diagram and schematic diagram of the fluorescence spectrophotometer, and you explain, okay, each of the steps. Okay, so or you can just write short notes on each of the uh, sections of the fluorescence spectrophotometer. So next we look at the factors affecting fluorescence. Remember, we've talked about fluorescence. So what are the factors that affect fluorescence? So even determine how it comes, intensity and all of that, and the wavelength where it falls. The wavelength actually determines the color, but we get to that when we in my last class on fluorescence. So the factors affecting fluorescence. One, molecular structure. So the question I can ask you is to identify or write short notes on the factors affecting fluorescence. So one, molecular structure. So to write short notes, you just talk about that. You can just start by saying that fluorescence depends on whether a structure has aromatic systems and conjugation, okay, as these enhance fluorescence. Or you can just simply write what is here, that aromatic systems and conjugation enhance fluorescence. What do we mean by this? When a material is fluorescent, okay, without conjugation aromatic, that can be, the intensity might be very low. But the more conjugation you have, okay, the more intense the fluorescence becomes. That means it becomes very brighter and brighter and you can see it clearly. So that means that kind of fluorescent material, you can easily use it for the applications we talked about earlier. So conjugation, remember conjugation means alternating single and double bonds, right? So that means you're having single, double bonds. So the more single, double bonds you have, then the more fluorescence is enhanced. Then um, rigid structures reduce non-radiative decay. So your structure should be rigid, okay, as this helps to reduce non-radiative decay. Now, solvent effect, this is another important factor. So some solvents are polar, some are not polar, right? So polarity alters emission wavelength. So emission wavelength in the sense that, okay, you can talk. Remember, I say wavelength also determines color. So whether it's going to be red, it's going to be blue. So the solvent you are using can determine that. Whether when you use water, you might get green. When you use another solvent, you might get a red emission. So that is important. Hydrogen bonding can also affect, can quench fluorescence. So hydrogen bonding is a big deal here. So when you introduce hydrogen bonding, fluorescence can be quenched. Okay, so that's something to consider. Temperature. So some fluorescent materials, okay, so can lead to quenching of the fluorescence. So fluorescence can effectively be quenched when you increase temperature. That means the material will stop becoming fluorescent. So it will stop exhibiting fluorescence. So temperature is a factor. pH, yes. So pH can also affect fluorescence. In some instances, pH can quench fluorescence. In some instances, it can enhance it. So it depends on the kind of molecule, okay, molecular structure too. So those are four factors, important factors that affect fluorescence. Now to quenching mechanisms. So how is fluorescence quenched? One, you have what we call it dynamic quenching. Dynamic quenching means the molecules, when they collide, okay, fluorescence can be quenched. When they collide, fluorescence can be quenched. And you have that um, equation. So then the Stern-Volmer equation, familiarize yourself with this equation because we'll be making use of it in my next class, where we'll be talking about how to use fluorescence to detect, okay, to detect something. So, so I'm going to teach you how to use fluorescence, okay, for detection. And then we are going to be looking at limit of detection, LOD. So in an exam condition, I can give you data and ask you to determine the limit of detection and to plot the to sketch the Stern-Volmer plot using this equation. So this equation, we are going to be using this equation as we move on. So you are going to be seeing more of this later. So take note of this. Now, remember I talked about static quenching, where the particles collide and then fluorescence is quenched. But you can also have that's for dynamic uh, quenching. So you have collision and then quenching. But for static quenching, so sometimes you can have formation of non-fluorescent complexes. So if there is a compound and then you are having maybe there's an impurity and that impurity leads to uh, formation of complexes that are non-fluorescent, then you have quenching. Or let's say there's a reaction, for instance, and when A attaches to B, okay, when A attaches to B, the product formed is non-fluorescent, then you can call that static quenching. Now, types of fluorescence spectra. So there's the excitation and there is the emission spectrum. So the excitation spectrum, here the emission wavelength is fixed, but the excitation is varied. So you can vary the excitation, okay, and then you can fix the emission. But for an emission spectrum, the excitation wavelength is fixed and the emission is scanned. So that is for emission spectrum. So take note of the two types. I will be giving you some examples of my own personal spectra as we move on. So then these are advanced fluorescence techniques, so I'll not be going deep into it, but these are very, very important. Okay. So there's the time resolved fluorescence. So here you are looking at how fluorescence is quenched or how it decays over time. So this is important in what we call sensing studies or detection studies. So for instance, you can use fluorescence to detect whether a molecule is present. You can use fluorescence to detect whether somebody is even sick in some instances. You can use fluorescence to detect whether there is an impurity in water or not. You can use fluorescence to detect whether there is poison somewhere or not. So so that is possible. So and then you can study it. Okay. Then we have the fluorescence resonance energy transfer. Okay. So where we look at distance dependent energy transfer. So these are more advanced fluorescence techniques. So now we move to applications in chemistry and nanoscience. So as I said, you can use fluorescence for trace detection. That's LOD. Okay. So you can use it to detect compounds. Okay. Either either in the body or that's a body fluid or something, or in the environment. Okay. So for instance, you can also use it to detect metal ions. So in the work I did some years ago, uh, I used carbon quantum dots. Is a fluorescent material to detect manganese and another one to detect mercury. So my students did that work some years ago. So they worked on fluorescent materials. So you can use a fluorescent material to detect whether something is present somewhere or not. So nanotechnology, yes. So this is my core area. I'm a nanotechnologist and I have produced carbon quantum dots. So you can Google that online. You see some of my work on that. So carbon quantum dots for sensing and imaging, right? So this is a work I did some years ago where I produced carbon quantum dots from, I'm sure you know this fruit. This is date fruit. Okay, so this is the juice. This is the juice. This is the carbon quantum dot I produced. So under white light, this is how it looks like. Under UV light, this is how it looks like. Under a stronger UV light, you can see it's green, very green. So it's green. It glows green, and I produced it from this. So this is work I've done. So you see some of this online. Then my students are also producing this year. So the final year students, I'm sure they don't know that it's fluorescent. I don't know. I'm not sure that it is fluorescent, but I'll test it. Okay, but they are producing this graphite carbon nitride. That's GC3N4. So I have about 6 students producing this year. So final year students. So they are using their own for photocatalysis. So some are doing photocatalysis, some are doing sunscreen and other things. So we see how that works. So fluorescent material is something I'm working on. So I'm not teaching you something that is is abstract. Now another application is detection of pollutants. Like I said, if you have pollutant in the environment, you can use it to know whether there's a pollutant here, there's a heavy metal here that can kill, that can lead to uh, poisoning. Okay, so and all of that. So you can use fluorescent chemicals to that. Then even biological system, you can use it to check to study protein folding. It is used in DNA intercalation assays. So that's the biological system. So the advantages, limitations. So one, yes, it is highly sensitive. So and sensitivity comes via wavelength tuning. Then it is a non-destructive analysis. That means when you are doing this analysis using the fluorescence photometry, it's not going to destroy your sample. So you can use it on the living cell. It's not going to destroy it. But the problem is that one, as a limitation, the fluorescence can be quenched. Okay, then you have photo bleaching. Photo bleaching means that sometimes the UV light you are using to create fluorescence can kill the fluorescence. So that's photo bleaching. They have matrix interference. So let's say you want to detect a particular thing in a sample. Sometimes another thing can also be detected, and then you have two things being detected at the same time, and then your detection can be wrong. So matrix interference. So these are summary of key relationships, and then yes. So the last on this fluorescence, we'll talk about it probably in class because it is much more technical. So I want you to uh, write your notes only on the aspect of fluorescence spectroscopy. Okay, what you have seen here, starting with fluorescence spectroscopy. So so put down a note on that, and let me have it by Friday. Okay, so I'll be marking your notes on Friday. So you start from fluorescence spectroscopy. Okay. So see you later. Have a wonderful um holiday, even though it's about to be over. So but all the same.